Okay, another perfectly inelastic collision, this time a little smaller scale. Okay, we're going to use two little mud balls. So two balls of mud collide head on in a perfectly inelastic collision. So let's suppose that these values are what are given: mass 1, mass 2, velocity 1 initial, velocity 2 initial. Okay, and so they all line up with our two masses here hurling at each other. Find the velocity of the composite ball of mud after the collision. So after these two guys jam together after the collision, we want to find the velocity of the two. Okay, so it's going to be just like the car problem. So we've got the same relationship. We've got separate masses and velocities on the left side. We've got the joint masses and one velocity on the right side. We solve it for the final velocity, and once this problem is set up, then we can start plugging our numbers in. So half a kilogram, 4 meters per second. Quarter of a kilogram at minus 3 meters per second. And then the two masses that are now joined together after the collision, a half a kilogram and a quarter of a kilogram. And so now we have, this case we didn't have we don't have zeros here, so we have to combine these two. So 2 kilograms meters per second minus 3/4 of a kilogram meter per second divided by 3/4 of a kilogram ends up giving us a final velocity of the two balls stuck together of 1.67 meters per second. Now we want to look at what is the change in the kinetic energy in this collision. Okay, again, these are perfectly inelastic collisions. Okay, so kinetic energy not conserved, right? So we want to look at the change in the kinetic energy. So the kinetic energy before the system collision is given by, here's our old standby relationships, kinetic energy initial is given by the kinetic energy of both of the balls, 1/2 mv squared added together. And so if we take that relationship, 1/2, half a kilogram, 4 meters per second squared, do the same thing with mass 2, 1/2, a quarter kilogram minus 3 meters per second squared, which gives us 4 and 1.125, that's like 1 1/8 kilogram meter squared per second squared. We can add those together because all our units match. We get 5.13 kilogram meter squared per second squared. Remember, I told you you're going to see these things resolved and decomposed and put back together. Gives us 5.13 Newton meters, which we now know a Newton meter is a joule, 5.13. So that is the kinetic energy of the system before the collision. Okay, the next one, they say the kinetic energy of the system after the collision then is what? So now we take the kinetic energy final, which is the two balls slammed together, 1/2 m1 plus m2 v final squared. We put our numbers in, half a kilogram, quarter of a kilogram, multiplied times now that 1.67 meters per second squared that we just solved for. When we run these together, we end up with 1.05 kilogram meter squared per second squared, or 1.05 joules of energy after the collision. So over here we had 5.13 joules of energy before the collision. Afterwards, we only had 1.05. So there was no conservation of energy. Okay? So we're going to stop here. This, if you're up to the lab, this is what your lab is going to look like, where we use the ballistic pendulum, fun lab, to do some collision type experiments and projectile experiments. Good lab.